Hello! We are moving on to different network flow problems, like the shortest dipaths and the maximum flow problems. The min-cost flow problem is a generalization of these problems. That is, these problems can be solved using min-cost flow problems. However, we will move away from network simplex and develop algorithms that are specifically designed for these problems, and those are efficient. We will still look at the LP and its dual to provide some inspirations for these algorithms. We now begin a section on the shortest dipath problem. Here is the problem definition. We are given a digraph D, arc cost W, and two distinct nodes S and T. And the goal is to find an ST dipath with minimum total arc costs. Here is an example of a digraph with some arc costs labeled. There are only three ST dipaths in this case. SAT has cost 6, SBT has cost 6, SABT has cost 5, so that is our optimal solution. Now let's look at an LP formulation for this problem. The first question is, how do we represent a dipath in variables? One easy way to do this is to set an arc to be 1 if it is in the dipath and 0 otherwise. Let P be an ST dipath. The characteristic vector of P is x, where xe is 1 if E is in the dipath and 0 if E is not in the dipath. Note that characteristic vector can be used to any subset of arcs, not just dipaths. For example, the characteristic vector for our dipath SABT is shown here. So arcs SA, AB, and BT has value 1, and arcs SB, AT have value 0. If we treat this as a flow, what are the net flows at each node? That is, what is inflow minus outflow? Well, at S, the net flow is minus 1. At T, the net flow is 1. And for everything else, the net flow is 0. So, we can make an LP as follows. The objective function is still minimize W transpose X, subject to the net flow x of delta V bar minus x of delta V is equal to minus 1 for S, 1 for T, and 0 for other nodes. And X is at least 0. Now this looks exactly like a transshipment problem, except the right-hand side is specified. So, now that you know how to take the duals of transshipment problems, can you take the dual of this LP here? We still have the same maximization, and the constraints are the same as before, minus yu plus yv less than or equal to wuv. But because the right-hand side of the primal is specified, we can now say that the objective function is yt minus ys. Once again, the constraint is equivalent to the reduced cost of uv is non-negative. The CS conditions are the same as before, either xuv is equal to 0 or the reduced cost of uv is equal to 0. So now let's see how we can prove that the dipath we had in our example is optimal. Our characteristic vector for the dipath has 1 on the arcs in the path. So SA, AB, BT are all arcs with positive flow. Using CS conditions, that means that these three arcs are tight arcs. So we should set ys to be 0, then ya becomes 3, yb becomes 1, and yt becomes 5. And now let's check the reduced cost of the remaining arcs. For arc AT, the reduced cost is 1, and for arc SB, the reduced cost is also 1. So both are at least 0. So what we have here is xp, the characteristic vector, is feasible. xp and y satisfy CS conditions, and y is feasible. So that proves that our solution is optimal. We can check that the dual objective value is yt minus ys, which is 5. And that is precisely the length of our ST dipath. Now this sounds like a pretty simple problem here with a pretty simple solution. It is just a specific example of the transshipment problem. But perhaps you might be feeling a bit fishy about this LP formulation. You might raise an objection about this formulation. So, what could go wrong with this LP formulation? Well, one problem is that it could have feasible solutions that are not characteristic vectors of ST dipaths. Take a look at this example here with a possible flow. We see that all the constraints are satisfied. The net flow at S is minus 1, net flow at T is 1, and the net flow at all the other nodes is 0. So this is feasible, but not an ST dipath. And that is a problem because normally, when we are looking at all possible feasible solutions of an LP, we think that all of them are eligible to be optimal solutions, and then we pick the best one. In this case, we cannot guarantee that the optimal solution we pick is actually representation of an ST dipath. So how do we know that an optimal solution to this LP must give us an ST dipath? As it turns out, this might not be a problem after all, and we will resolve this in the next lecture.